In this example, we are asked to compute the divergence and the curl of this given vector field. So let's start with the divergence. You might remember, I hope, that the divergence of f is equal to the gradient operator dotted with the vector field f. And so, how does this work? Well, this ends up being the sum of the component partial derivatives. So if this first component is p and the second component is q, we'll call the third component r. Then the divergence of this vector field is just the partial derivatives of the component functions with respect to the variable, the component that they're in, and then add them all up. So dp dx plus dq dy plus dr dz. So let's start with computing this one. We find the divergence of f is then these are just going to be some chain rules if necessary even, but notice that neither p does not depend on x, right? So there's no x variable here, so the x derivative of p is 0. Same thing here, q has no y's in it, so this is a constant with respect to y, so that's 0. And same thing with r. R has no z's, so its z derivative is also 0. And so the divergence of this vector field is 0. So when a vector field has 0 divergence, we call that vector field incompressible. So incompressible when the divergence is 0. All right, let's move on to the curl of this vector field. Let's take a look at it. So the curls, I left the curl for a second because the curl is a little bit different. So remember that the curl of a vector field, there's a formula for it. The curl measures the rotation of the vector field, and the curl, the way I'm going to compute it, is the cross product of the del operator with the vector field f. And so the way that we're going to compute this is if this is I, j, k, I'm working out the cross product here. The components of the second row of the cross product are then d by dx, d by dy, d by dz, and I'll leave these in the simplified lazy notation. And what we want to do is then apply that to this vector field. So I'm going to write these functions in here. This one's log of 2y plus 3z. What I need to do is give myself more room here. So that's what I'll do. So, and then the second component, this q component, is the natural log of x plus 3z. And finally, the r component is the natural log of x plus 2y. Now, when we take the cross product here, we actually compute the curl. Let's see what happens. The first thing is we start in the I component, and always remember that even though we kind of draw the picture like an x like this, if there's derivatives here, if this is a symbolic cross product, then the derivatives have to operate on the functions, the relative functions here. So this one's going to be the y derivative of our natural log of x plus 2y minus the z derivative of the natural log x plus 3z, and that's the I component, okay? These are, again, my notation for the partial derivatives here. The next thing that we want to do is move on to the j component. J component goes the other direction, so this one's going to be the z derivative of the natural log 2y plus 3z minus the x derivative of natural log x plus 2y. We're going to have to compute these, right? But let me just get it all written out. And again, poor planning here. Let me get some more room so I can get this all in one line. And then the last one is the k component. The k component here is going to be the x derivative of the log of x plus 3z minus the y derivative of the p component function here, so 2y plus 3z. And now we just need to compute all of these. Each of these derivatives is going to be, I'm going to put this actually into vector notation, but each of these derivatives is going to be a chain rule, and the chains are not going to be too crazy, so let's just write it out here. This one's going to end up being 2 over x plus y, that's the y derivative here, minus the z derivative of this one is 3 over x plus 3z. Okay, we go to the next one. the z derivative in the j component. Notice I already flipped the order here, so there's no minus sign here. If you're just copying down a formula, there might be a minus sign here. But here we have the z component is going to be 3 over 2y plus 3z minus, this is then going to be the x derivative, so 1 over x plus 2y. Okay, and then in the last component we have the x derivative here, so that's 1 over x plus 3z minus the y derivative of this one, which is 2 over 2y plus 3z. And we could leave it like this. There's nothing wrong with this, but I want to simplify this out, add up the component functions. Remember, this is a vector field, so we can't cross the components here, right? We can't move from one component to the other and try to simplify stuff that way. We can only add up what's in the individual components themselves. And so let's see what happens. When we add this one up, we get 2x plus 6z minus 3x minus 3y all over the product. I'm not going to multiply these out, but x plus y times x plus 3z. So there's the component function in the x component slot of the curl vector field. On this one we have 3x plus 6y minus 2y minus 3z all over the denominator of this one is 2y plus 3z times x plus 2y. And then finally on this one we have 2y plus 3z minus 2x minus 6z all over this denominator, x plus 3z times 2y plus 3z. Okay, and one last step here, we'll call it after this, but we can combine some like terms here. We're going to end up with minus x minus 3y plus 6z all over this denominator. Again, I'm not going to multiply out the bottom here. You can do that if you want to. But I'm just going to combine the like terms on the top. So this next one's going to be 3x plus 4y minus 3z. And that, notice each of these have a different denominator. So that's interesting. And then finally here we have minus 2x plus 2y minus 3z. And its denominator is x plus 3z times 2y plus 3z. And this is the curl of our given vector field. Okay, so zero divergence, that meant incompressible. That's just a term we use when the divergence is 0. And the curl, non-zero, the curl was given by this vector field here.